Hello everyone, I Kamini Rathore, Assistant Professor, RCET, CSVT Bhilai, welcome you all in SWAYAM online course, Essentials of Surveying, Applications and Techniques. Today we will discuss lecture number 20, that is Contouring Part 2. In this lecture, we are going to learn about interpolation of contour, contour gradient, uses of contour maps. After that, we will also discuss the topo sheet. Let's begin by exploring the concept of contour interpolation. The process of drawing contour proportionately between the plotted ground points or in between plotted contours is known as interpolation of contour. Interpolation of contours between points is done assuming that the slope of the ground between any two points is uniform. It may be done by one of these methods, such as by estimation, by arithmetic calculation and by graphical method. Let us see first method, which is by estimation. The position of the contour points between ground points are estimated and the contours are then drawn through them. This method is rough and the accuracy depends upon the skill and experience of the surveyor. It is usually used for contouring small scale maps. The method of contouring of topographical map on scale 1:50,000 in the Survey of India is generally based by method of estimation. Let us see the procedure of this method. Height of the selected ground points are calculated by reading clinometric readings and multiplying by their scale distances from the plane table position. Plant positions of the heighted points are surveyed by normal method of plane tabling. In between these points, contours are interpolated, keeping in view the nature of the ground, and an experienced surveyor draw contour without any serious error. Let us see the second method of contour interpolation, which is by arithmetic calculation. In this method, positions of contours between two known points are located by making accurate calculations. Hence, the method, though very accurate, is time consuming and laborious. It is generally adopted when higher accuracy is demanded for a limited area. You can see in figure 1, suppose A, B, C and D are 4 plotted points at 2 cm apart and their ground reduced levels are 57.5, 63.2, 68.2 and 59.2 meter respectively. It is required to draw contours at 2 meter vertical interval. For example, let us see interpolation along AD. See the figure number 1. Here the total difference in elevation between A and D is 59.2 minus 57.5 equal to 1.7 meter. The difference of level between A and 58 meter contour is 58 minus 57.5 equal to 0.5 meter. Hence, the distance of the 58 meter contour from A equal to 0.5 divided by 1.7 into 2 centimeter equal to 5.9 millimeter. Again, interpolation along AB. The total difference in elevation between points A and B is 63.2 minus 57.5 equal to 5.7 meter. The difference of level between point A and the 58 meter contour is 58 minus 57.5 equal to 0.5 meter. Hence, the distance of the 58 meter contour from the point A along AB is 0.5 divided by 5.7 into 2 equal to 1.8 millimeter. Similarly, the distances of the 60 meter and 62 meter contours from the point A can be calculated. This will be 2.5 divided by 5.7 into 2 equal to 8.8 millimeter, and 4.5 divided by 5.7 into 2 equal to 15.8 millimeter respectively. Let us see interpolation along BC. The total difference in elevation between points B and C is 68.2 minus 63.2 equal to 5 meter. The difference of level between point B and the 64 meter contour is 64 minus 63.2 equal to 0.8 meter. Hence, the distance of the 64 meter contour from the point B along BC is 0.8 divided by 5 into 2 equal to 3.2 millimeter. Similarly, the distances of the 66 meter and 68 meter contours from the point C will be 2.8 divided by 5 into 2 equal to 11.2 millimeter and 4.8 divided by 5 into 2 equal to 19.2 millimeter respectively. Again, let us see the interpolation along CD. The total difference in elevation between points D and C is 68.2 minus 59.2 equal to 9 meter. The difference of level between point D and the 60 meter contour is 60 minus 59.2 equal to 8 meter. Hence, the distance of the 60 meter contour from the point D along DC is 0.8 divided by 9 into 2 equal to 1.8 millimeter. Similarly, the distances of 62 meter, 64 meter and 66 meter and 68 meter contours from the point D can be calculated. This will be 2.8 divided by 9 into 2 equal to 6.2 millimeter, 4.8 divided by 9 into 2 equal to 10.7 millimeter, 6.8 divided by 9 into 2 equal to 15.1 millimeter and 8.8 divided by 9 into 2 equal to 19.6 millimeter respectively. The points having equal elevations are joined and the required contours of 58 meter, 60 meter, 62 meter, 64 meter, 66 meter and 68 meter may be drawn. To achieve better accuracy, interpolation along the diagonals AC and BC may also be done. Then the contours are drawn through the points of equal elevation. Let us see the third method of contour interpolation, which is graphical method. In this method, actual calculation for interpolation of contours between known heights is not done, but the locations of the contours are obtained graphically with the help of a tracing paper or tracing cloth. There are two methods. First one is by drawing radiating lines and second is by drawing parallel lines. Let us see the first graphical method of interpolation. In this method, several lines are drawn parallel to each other on a piece of tracing paper. See figure number 2 and let the interdistance between the lines be 2 mm. Every fifth line may be drawn heavier to facilitate easy contouring. Suppose we have to interpolate contours at 2 meter vertical interval between 2 points A and B whose elevations are 112.5 and 127.5 meter. Let the bottom line on the tracing paper represent 110 meter, whereas other lines represents every 2 meters. Place the tracing paper on the plan on which heighted points have been plotted in such a way that the line representing 112.5 meter, in this case a point in between the two lines 112 meter and 114 meter and at 0.5 mm from 112 meter line passes through the point A. Now rotate the tracing paper about the point A till the line representing 127.5 meter. In this case, a point in between the 126 meter and 128 meter lines and at 0.5 mm from 128 meter line is made to pass through the point B. Prick through the points of intersections of the ruled lines on the line joining the points A and B to get the required positions of the desired contours. It may be noted that the same set of ruled parallel lines may be utilized to interpolate contours between other points. It may be noted that the same set of ruled parallel lines may be utilized to interpolate contours between other points, so long as the distance between them is greater than the perpendicular distance between lines representing 112.5 meter and 127.5 meter. In case the distance is less, then another set of value are to be given. Assume that each line represents 3 meter, so that the bottom line and every fifth line thereafter represents 110, 125, 140 meter, etc. Now the distance between points, which was less in earlier case, is more than the perpendicular distance between the lines representing 112.5 meter and 127.5 meter. Rotate the tracing paper so that 127.5 meter line is made to pass through the point of 127.5 meter. Similarly, interpolation between other points of different height may be made by assigning different values to the ruled line. After interpolation between the points has been done, the contour lines are drawn through the points of equal elevations. Let us see the second graphical method of interpolation. You can see in the figure 3, a line xy of any convenient length is drawn and divided into small equal parts, say each 2 mm width on a piece of a tracing paper. At its midpoint, a perpendicular is erected and a pole O is so chosen on the perpendicular that the angle YOX is approximately equal to 45 degree. Draw radial lines through pole O and division marks on the line XY. Rule out few lines parallel to XY across the radial lines. Such lines which serve as a guide are generally known as guide lines. It can be easily verified that these lines are equally divided by the radial lines. The first radial line and every fifth line thereafter are drawn a little heavier or bolder to facilitate quick reading of the diagram. Let us assume that we have to interpolate contours at 2 meter vertical interval between points A and B, whose elevations are 114.5 and 137.5 meter. Let us assume that we have to interpolate contours at 2 meter vertical interval between points A and B, whose elevations are 114.5 meter and 137.5 meter. Assume Y to read 110 meter and every fifth line 10 meter apart. Place the tracing paper over the plan such that the 114.5 meter and 137.5 meters radial lines simultaneously pass through the point A and B below the tracing paper. The points at which radial line of 116, 118, 120, 122, 124, 126, 128, 130, 132, 134 and 136 meter intersect the line AB may then be pricked through to get the positions of required contours on the plan. In a similar way, interpolation between other points may be done and contour lines drawn through the points of equal elevation. Let us move on to the next topic of today's lecture, that is contour gradient. The imaginary line laying throughout on the surface of the earth and preserving a constant inclination to the horizontal is known as contour gradient. The inclination of a contour gradient is generally given either as rising gradient or falling gradient and is expressed as the ratio of the vertical height in a specified horizontal distance. Suppose the bed of a canal is lowered by 1 meter in a length of 100 meters, then the gradient is 1 in 100. Similarly, when a railway track rises 1 meter in every 250 meters of its length, the inclination of the contour gradient is 1 in 250. If we know the inclination of the contour gradient, its direction may be easily located on the ground by using one of the following surveying instruments. First is Indian tangent clinometer, second theodolite, third is level and fourth is Ghat tracer. First of all, we will see locating a contour gradient with an Indian tangent clinometer. See the figure number 4. The clinometer is placed on a plane table which is centered over the point A, from where the direction of the contour gradient is required to be located. The natural tangent of the angle of elevation for a rising gradient or the angle of depression of a down gradient is calculated, that is tan theta equal to vertical height difference of the points divided by horizontal distance between the points. The clinometer is leveled and the line of the sight is clamped on the natural tangent readings for the given radian. For an example, the natural tangents for 1:100, 1:200 and 1:250 are 0.01, 0.005, 0.004 respectively. Another person holding a ranging rod with a target fixed at the height of the eye hole of a clinometer is directed to move up and down the slope till the target is bisected by the line of the sight. The point B is pegged on the ground. The instrument is then transferred to the point B. Other points C, D, etc. on the contour gradient are located in a similar manner. It may be noted that the line of sight at points A, B, C, D, etc. remain parallel to the lines joining the points AB, BC, CD, etc. Let us see locating a contour gradient with a theodolite. For this, see figure number 5. The theodolite is centered and leveled over the starting point of the contour gradient. The reading of the vertical circle of theodolite is set to the required angle of slope. Now, the telescope points in the required direction of slope. Telescope is then swing in the direction of the proposed alignment of the canal or road. The height h of the Turnerian axis of the theodolite is measured accurately and a target fixed to a rod at the same height is sighted. When the target is bisected by the horizontal crosshair of the telescope, the position of the target rod is the required point on the contour gradient. For accurate work, a leveling staff is sighted instead of a target. The instrument is then shifted to the point so obtained on the contour gradient and the line of slope is extended further. Let us see locating contour gradient with a level. The level is set up over any commanding position, but not necessarily on the desired contour gradient. The height of the line of collimation for this setting of the instrument is determined by reading a leveling staff held on a nearby benchmark. The reduced level of the first point on the contour gradient is then obtained by reading a leveling staff. If the reduced level of the line of collimation is 501.655 and the reading on the staff held at the starting point A is 1.655, then the reduced level of a point A is 501.655 minus 1.655 equal to 500 meters. Now, to locate another point B on a falling contour gradient 1:100, direct the staffman to walk along the proposed alignment so that it is 20 meter away from A. The reading on this point should therefore be 1.655 plus 0.2 equal to 1.855 meter. Fix a wooden peg into the ground such that the reading on the staff when held on the top of the peg is 1.855 meter. The top of the wooden peg is on the contour gradient. The staffman is again directed to move to a point C, 20 meter away from B and in the same straight line. Now, the reading on staff must be 1.655 plus 0.4 equal to 2.055 meter. Let us suppose that the staff reading at C is 1.755 meter. The staffman will be directed to diagram a pit such that the reading on the staff when held vertically becomes exactly 2.055 meter. In this way, a number of points of the contour gradient are located before actual construction of the road or railway may be started. Let us see locating a contour gradient with a ghat tracer. The wooden stand on which the ghat tracer is suspended is held on the starting point of the desired contour gradient. The height of the sighting tube above the top of the peg driven at A is measured accurately with a tape. A target is then fixed on a rod at the same height as the height of the sighting tube above the ground level at A. The target man is then directed to walk along the line joining the starting and closing points on the contour gradient. The beveled edge of the weight is then kept at the falling gradient 1:100, so that the line of sight of the instrument becomes parallel to the gradient. Sighting through the eye hole, direct the target man to move up and down along the line till the target is bisected accurately by the intersection of the cross wires. The staffman marks the position of B at the foot of the target rod. The instrument is then shifted to B and the procedure is repeated to fix another point C. In a similar manner, other points are fixed en route till the last point is located. Let us see the next topic, which is uses of contour maps. Contour maps are used for the various purposes. First is to study the general character of the tract of the country without visiting the ground. With the knowledge of the characteristic of the contours, it is easier to visualize whether the country is flat, undulating or mountainous. It is also used to decide the most economical and suitable sites for engineering works such as canals, sewers, reservoir, roads and railway, etc. It is also used to determine the catchment area of the drainage basin and hence the capacity of the proposed reservoir. It is used to compute the earthwork required for filling or cutting along the linear alignment of projects such as canal, roads, etc. It is used to ascertain the intervisibility of points. It is also used to trace a contour gradient for the road alignment. It is also used to draw longitudinal sections and cross sections to ascertain the nature of the ground. It is used to calculate the water capacities of reservoir. It is used to decide the best positions of the guns, the line of march and camping grounds by the army commanders during wars. Contour maps are extremely useful for various civil engineering works such as drawing of sections, selection of a canal alignment, determination of intervisibility, tracing of a contour gradient, measurement of catchment area and calculation of storage capacity of reservoir. Let us go through each of these one by one. First is drawing of sections. On a contour map, sections in any direction may be drawn to study the general shape of the ground. Such sections are also required for calculating the earthwork needed for road, railway or canal project. Let it be required to draw a section along the line PQ. Plot the points at which various contours intersect the line PQ along x axis and their corresponding heights are plotted along y axis to any convenient scale. The ends of the perpendiculars representing the contour heights may then be jointed by smooth straight lines to give the configuration of the ground surface. For this, you can see figure number 6. Second is selection of a canal alignment. Suppose a reservoir is to be constructed at R across a river. An irrigation canal reduced level is required to be constructed to irrigate the area of two villages, Rampur and Shampur, located on opposite slope of the ridge. We know that water in canals flows under gravity. From the contour map, see figure number 7, it may be noted that the elevation of the reservoir site R is 547 meter approximately. The canal alignment should therefore be kept below this level. The watershed or ridge line is first marked by a dotted line. From R, the canal is taken along RS, where S is a point on the watershed line and its height is approximately 542 meter. Points may be chosen by considering the other factors to avoid construction of aqueducts over the intercepting drainage en route. From S onward, the canal may be aligned along the watershed line STPL, ensuring proper gradient. Branch canals may then be constructed on either slope so that the area of both the villages may be irrigated. It may be noted that in the absence of a contour map, the layout of the canals cannot be decided economically. Third is determination of intervisibility. Intervisibility between two points situated on different elevations with no intervening raised ground may be ascertained by inspection from the map. Let A and B be two given points whose elevations as obtained by interpolations of contours are 645 and 628 meters respectively. To ascertain the intervisibility of the points A and B, join A and B by a dotted pencil line. By inspection of the contours intercepted by the line AB, it is seen that contour value decreases up to C and then increase up to point B, as no higher value contour appears in between. The points A and B are intervisible. When it is not quite evident from the inspection of the map whether two points are intervisible or not, intervisibility may be ascertained by joining the given points by a straight line, and note down the values of the intervening contours on this line. For this, you can see figure number 8. Fourth is tracing of a contour gradient. See figure number 9. On a contour map, the alignment of a proposed road or railway may be decided and located by drawing a contour gradient. Let the contour interval on the supplied contour map be 10 meters and an upward gradient 1 in 30 is required to be drawn from A to B. Ground horizontal equivalent equal to contour interval into gradient equal to 10 into 30 equal to 300 meter. With A as center and a radius representing 300 meters on the scale of the map, draw an arc to cut the 60 meter contour at A. Similarly, with A as center and with the same radius, draw another arc to cut 70 meter contour at B. In a similar manner, points C and D are obtained. When an arc with D as center is drawn, it cuts 100 meter contour at E dash. Point E dash through in the continuance of the route is rejected because D and E dash when joined cuts the 100 meter contour again, and thus a deep cutting is involved. At E, the arc of the same radius if drawn cuts 110 meter contours nowhere. To overcome this difficulty, the 105 meter contour is interpolated and half the radius is used to obtain the point F. Location of a number of points are made till the last point is reached. During the process of drawing arcs, it may be noted that it cuts next higher contour at 2 points. Only the point suitable for the proposed alignment, considering the general layout and geological features, is accepted and the other points ignored. During construction, the route of the road is made to follow the contour gradient line, so obtained as closely as possible. Fifth is measurement of catchment area. See figure number 10. The area of the tract of a land which contributes water which flows over the surface of the earth into a stream at any point A is called catchment area. The limit of such an area may be marked sufficiently accurate on a contour map. The line that mark the limits of drainage area possesses the following characteristics. First is, the line follows the highest ridge line and divides the drainage area from other area. Second is, it follows the ridge. Third is, it is everywhere perpendicular to the direction of the contours. An imaginary line possessing these characteristics is generally known as watershed line. A line is drawn on the map with dashes and dots to mark the bounding limits of the catchment area. The plan area is then determined with the help of the planimeter. The contour map is also used for calculation of storage capacity of reservoirs. The capacity of a reservoir at its dam site may easily be calculated with the help of a contour map. Knowing the maximum water level of the dam and contour interval, the area enclosed at respective elevations may be found out by the planimeter. The capacity of the reservoir may then be computed by using trapezoidal or prismoidal formulae. So, in this lecture we have discussed about interpolation of contours, contour gradient, uses of contour maps and topographical maps. We have also discussed how to read topo sheet. In the next lecture, we will discuss about plane table surveying. With this, we will end today's lecture here. Thank you for your patience. Thank you.